So we have looked at phase changes of liquids and gases in a little bit of depth. And now we'll take a look at some more phase changes involving solids. The first thing that we would think of is melting. And another name for that is fusion. So that's when we go from a solid to a liquid. And we saw before that vaporization, which is changing a liquid to a gas, has a thermodynamic value called the heat of vaporization, or the enthalpy of vaporization. There's a similar one for fusion or melting, the heat of fusion or enthalpy of fusion. So the molar enthalpy of fusion, molar meaning 1 mole, is the heat required to melt 1 mole of a substance. And if you recall, enthalpy of vaporization was a great indication of relative intermolecular force strengths. So in this table, the substances are organized in increasing heat of vaporization values, which also indicates the intermolecular force strengths. Of course, you can see that methane, for instance, is a small molecule, non-polar, only London dispersion forces. Water, similar size molecule, similar molar mass, hydrogen bonding. Much stronger intermolecular forces as seen in the higher enthalpy of vaporization. Sodium bromide is actually an ionic compound, so you have sodium cations and bromide anions in the crystalline lattice, and it takes a very significant amount of energy, relatively speaking, to move that substance into the gas phase. The enthalpy of fusion compared to the enthalpy of vaporization for a substance, the fusion value is much smaller. So why is that? Well, with fusion, you're melting. The molecules are in a crystalline lattice, and then they become unstuck in terms of being locked in relative locations to one another. And in the liquid, now they are free to move about, but they are still in contact with one another. The intermolecular forces are still holding the particles together. When we vaporize a substance, we are overcoming the intermolecular forces completely and separating the molecules from being in contact with one another in a liquid phase to make them independent particles in the gas phase. You can see that the enthalpy of fusion is not as reliable in comparison of relative strengths of intermolecular forces. Take propane and methanol, for instance. You can see that methanol has stronger IMF compared to that of those of propane. The intermolecular forces are stronger in methanol than they are in propane, and that's reflected in the enthalpy of vaporization being higher. But methanol has a lower heat of fusion than does propane. So the trend is not reflected in the enthalpy of fusion values. This is because we are not completely overcoming the intermolecular forces to separate the molecules, and the change that is taking place is that of a solid to a liquid, which introduces another variable, actually, the crystalline lattice. The different substances have different crystalline lattices. The molecules in whatever crystalline lattice they are in have different packing efficiencies, the ability to get into that particular lattice might be easier for one molecule than it is for another. And that's a whole nother variable outside of relative strengths of intermolecular forces. So heat of fusion is not really a very strong indication of relative intermolecular force strength. Of course, these heats of vaporization and heats of fusion can be used in calculations. So in this problem, it is asking to calculate the heat required to melt 120 grams of water. So the heat of fusion of water is 6.01 kilojoules per mole. So Q for melting, Q is heat, is equal to the number of moles times the molar enthalpy of fusion. So if we had 1 mole, it would take 6.01 kilojoules to melt it. But we have 120 grams. And another thing we might want is the molar mass, which you can use your periodic table or look it up. So 1 mole is 18 grams. If we have 120 grams, we have more than a mole. How do we do this? Q, the heat required to melt, is going to be the number of moles times the kilojoules per mole. But we don't have moles, we have grams. 120 grams. So to convert that to moles, we'll use 18.02 grams is equivalent to 1 mole. And that will give us moles. And then if we continue on, for every mole we need 6.01 kilojoules. So just rounding off, 6 over 18 is 1/3, and 1/3 of 120 is 40. And actually, if you use a calculator, we should go 3 sig figs, because 120 has 3 sig figs, so it's 40.0 kilojoules. The next question says to calculate the heat required to melt 120 grams of water, which we just did, and raise its temperature from 0 to 10 degrees. If you remember, you probably saw heating curves before. As you add heat, you raise the temperature. And so we are going to go from 0 to 10. So as you add heat, the temperature raises. But before that, that's the liquid water. But before that, we melt it. And what happens when you melt? You do not change the temperature. And so Q melt was 40 kilojoules. We've already calculated that part of it. This part is 40. And now we got to calculate this part. How much to raise the temperature from 0 to 10. So Q warming, well, if you remember from Gen Chem 1, that will be ms delta T, where M is the mass, S is the specific heat, delta T is the change in temperature. And the specific heat of water is 4.186 joules per gram degrees Celsius. So Q, I'll abbreviate this warming as warm. That's going to be 120 grams times 4.186 joules per gram degrees Celsius. And the change in temperature, it's the final minus the initial. So this difference here is going to be 10. So if we do the math, you can use the calculator. I'll write it in scientific notation. It's about 5,000 joules, or if we convert that to kilojoules, it's 5.02 kilojoules. So Q total will be Q melt plus Q warm, which is 40 plus 5, we get 45. Only one decimal place in our answer. So just a reminder, you probably saw heating curves in Gen Chem 1, and as you add heat, you could warm a solid, and adding heat will change the temperature, and then this would be melting. And then here we would be changing the temperature of the liquid after it melts as you continue to add heat. And then you would get up to the boiling point. Here's the melting point temperature and the boiling point temperature. You call those normal melting and boiling points if you're under 1 atmosphere. Of course, they could be different if you have a different atmospheric pressure over top. Then this would be boiling, and the heat you add would go into that phase change, changing liquid to a solid. And then once it's all changed to a vapor, you're increasing the temperature of the gas. So here we see that same generic heating curve with some more detail in region 1 where we have a solid. The heat input into the system increases the temperature. In part 2 of this diagram, we have melting or fusion, and there the heat is used to melt the solid, and there is no change in temperature. We use the enthalpy of fusion. And then region 3, where we have a liquid, the heat input increases the temperature of the liquid, and we use the specific heat whenever we raise the temperature of a solid or a liquid or a gas. In region 4, we have vaporization, and in that region, the heat is used to evaporate the liquid and form a gas. There is no temperature change. And then finally, in region 5, we have a gas, and we are just raising the temperature when we add heat, and we use the specific heat of the gas. You might see a subtle difference in the slopes of regions 1, 3, and 5, where the temperature is changing, and that's because we have different specific heat values. So the specific heat of the solid, liquid, and gas, those 3 specific heat values are not the same, and so the slopes will be slightly different. If you have a problem where you start with a solid and you raise the temperature and then it melts, and then you raise the temperature of the resulting liquid some more, you might be asked to calculate the heat required. Well, that is 3 steps. The temperature change of the solid is due to some heat input. The phase change is due to some heat input. And then finally, the temperature change of the resulting liquid is due to further heat input. So this would be the total amount of heat added. You have to be aware of exothermic and endothermic processes. Going from left to right on this graph is an endothermic process. If we increase the temperature, that's pretty obvious. We get positive 10 for delta T. The final temperature is higher than the original, and that's endothermic. If we go, say, from 30 to 20 degrees Celsius, we're going to have a negative delta T. That's cooling, and that process is exothermic. This equation, Q equals ms delta T, has a sign on Q. Remember, if Q is positive, it is endothermic. And the sign on Q will come about from the sign on delta T. If you have a warming of a substance, the temperature is increasing, that's endothermic. Delta T will be positive and Q will be positive. If you have an exothermic process, delta T will be negative and the resulting Q will be negative. When Q is negative, that's exothermic. But when you use these equations where you relate the heat input to the quantity of matter undergoing the phase change, you use delta H, enthalpy of vaporization or enthalpy of fusion. But these are all defined as endothermic. So you have to kind of be aware, what is an endothermic process? Liquid to gas, solid to liquid. You supply the sign on Q. If you have an exothermic process, the reverse, you have to be aware of it. Solid to liquid, gas to liquid. Those changes are exothermic and Q is negative. Finally, one more illustration of a heating curve is what we see here. And this one is for 1 mole of water going from minus 25 Celsius to 125 Celsius. What you see here are the different slopes. I think those are clearly illustrated. But then also, the magnitude of Q is more accurately represented in this diagram. Q for vaporization is going to be much larger than Q for fusion because the enthalpy of vaporization is so much greater. It requires so much more energy per mole to vaporize a substance than it does to liquefy a mole of the solid of that substance, because you are completely overcoming intermolecular forces when you vaporize the substance. The other phase change is solid to gas. And the molar enthalpy of sublimation is the heat required to sublimate 1 mole of a substance. So that's the heat of sublimation. So you can see here enthalpy of sublimation, and this process going from a solid to a vapor in 1 step, that's sublimation. But you could also envision it happening in 2 steps, where you have fusion and you have vaporization. Delta H sublimation is equal to delta H fusion plus delta H vaporization. And this is, if you recall, that is Hess's law. That states that for a state function like enthalpy, you can take 2 different paths and the net result will be the same. So delta H total is the same if you do it in 1 step or 2 steps. If you measure these values carefully, very, very carefully, this statement is not going to work out perfectly because these values, when you see the degree sign here, that's saying what the enthalpy values are under standard thermodynamic conditions, which among other things is 25 degrees Celsius. And probably if you do these measurements, you're not at 25 degrees Celsius for the fusion, the vaporization, sublimation. So you'll get some values that are non-standard, and so the sum of the fusion and vaporization heats or enthalpies will not equal that of the sublimation perfectly. Because there is a slight temperature dependence, you'd have to measure very carefully to see it. Enthalpy values are fairly constant over a wide range of temperatures though. So if you recall, we looked at enthalpy of vaporization. It came up in the Clausius-Clapeyron equation, and it was part of the slope of the linear form where you graph natural log of the vapor pressure versus 1 over T. And the slope of the line was minus delta H vaporization over R. Technically, if you change the temperature, delta H changes, but it's such a small amount that you can treat that as a straight line with the Clausius-Clapeyron equation.